Bismillahirrahmanirrahim. And dear students, we are here with the A part of lecture number 5. So let's begin where we left in the last lecture. We were discussing the types of operations which any microprocessor has. These, you can say that these are the categories which has multiple opcodes available. So in this category, usually classified into operations, usually classified into groups, and an example categorization is arithmetic instructions, means it relates to the integer arithmetic. Logical instructions, it is also called boolean instructions. Data access and transfer instructions, this is another group. Conditional and unconditional branch instructions, this is one more group. Floating point instructions, which relates to the floating point values, and the processor control instructions. So these we had discussed in the last class, and let's continue the same topic in the further detail. Okay, the computer has a special register which is also called a program counter, because it is a hardware register. So it is used during fetch execute cycle. As I told you that in the chapter number 4, that doesn't matter that how complicated or how complex a program is, at some point of time every computer program, it runs in a fetch and execute cycle. So this program counter is used in the fetch execute cycle. And how does this work? That it gives address of next instruction to execute. Okay, and it is also named as instruction pointer. So few books would be calling it program counter, and others would be calling it instruction pointer. So there is no difference between these two. And these are the synonym terms of each other, which can interchangeably used for the same purpose. That is, the program counter is equal to the instruction pointer. These are the same thing. And here is a specimen fetch execute algorithm details. Okay, look, that assign the program counter an initial program address. So you think of it like this, that when we boot the computer, the program counter is always at 0, because it needs to start booting from the scratch. So program counter, it remains on 0, and then it proceeds further. And repeat forever means repeat this code forever. Fetch, access the next step of the program from the location given by the program counter. That the value which the program counter is having in its register, access that value, and then see that what is the next step at that value, and fetch it, decode it, and set an set an internal address register A, which would be the address register, to the address beyond the instruction that was just fetched. This is the address register which is used to copy the addresses, and it is useful when we use the jump instructions, or the conditional jumping, or unconditional jumping. So address register is the most valuable and mandatory register in any computer execution. So execute, first fetch and then execute, perform the step of the program, that whatever instruction is there on that address, whatever instruction is there, whatever opcode is there, just perform that operation and copy the contents of address register A to the program counter. And then by adding, normally it adds +1 in the program counter. So if the computer is restarting from the scratch, so it would be 0, and then it will proceed like 1, 2, 3, and so on. And this is the role of the address register. And now let's discuss a few things about branches and the fetch execute cycle. Okay, there are two types of branches. One is called absolute branch and the other one is called the relative branch. In absolute branch, typically we deploy this type of branching by jump command. In the code, we use the jump keyword to jump to the branch, and operand is an address. Its operand is an address assigns operand value to internal register A, and what it does, that it assigns that operand's value to the address register. So this is called the absolute branch. And the other one is the relative branch. The second type of the branch is the relative branch, and we deploy this, or we call this relative branch by uh, using the keyword br, typically named br. And in this case, the operand is a signed value. In the last absolute branch, the operand was an address, and in the case of relative branch, the operand is a signed value, and we add this operand value to internal register. Okay, in the absolute branch, we just assign that operand value to internal register, but in the relative branch, we add this value to the internal register. In that case, it will jump forward or backward and perform the relative branch. Okay, and subroutine. What is subroutine? It is also a jump subroutine or JSR. And so we use this instruction through JSR instruction, and it is very similar to a jump instruction which we discussed on the last page, absolute branch. So the jump subroutine saves value of internal register A, replaces A with operand address, and return from subroutine. How do we return from the subroutine? By the RET instruction, or by using the keyword RET in the code. It brings the computer out of the subroutine, and then it comes for the main processing and available for the main processing. So retrieves value saved during JSR. When we called the subroutine, the computer had copied and saved the internal register A contents. So when the return from subroutine command or the RET instruction is given to the program and to the computer, it retrieves value saved during JSR, and replaces A with the saved value, and it replaces A, and A means the address register, with the save value. So in this way, we call the subroutines and jump commands. And how do we pass the arguments? Passing argument is another issue. There are multiple methods which have been used for this purpose, and examples include the store arguments in memory. We can store arguments in special purpose hardware registers, and as well as we can store arguments in general purpose registers as well. And many techniques also used to return results from function. So these are the arguments, and we will further look into it, that how do we use these arguments. The next thing is the register window. As we have discussed, that internal room available for the execution of instructions in the memory on chip is very limited. So we have a concept of register window to fulfill our overwhelming demand within the limited resources. So this is the same concept, as we can say it, a sliding window mechanism in the TCP or the transmission control protocol in the internet. The register window, how does it work? That hardware optimization for argument passing. It is a hardware optimization for argument passing, and the processor contains many general purpose registers. Only a small subset of registers visible at any time. Not all the general purpose registers are visible at all the time. Only a small subset, that it's a small subset of registers visible at any time. Caller places arguments in reserved registers, and during procedure call, a register window moves to hide old registers and expose new registers. The last thing which is written here, you can easily understand it by carefully looking on this picture. This is the illustration of the register window. You can see that it has multiple registers available, contiguous registers, and during the normal operation, when the program runs, the registers 0 through 7, this downward bracket is used, that as subset of the total registers is used, and during the subroutine call, the register numbers 0 through 7, it slides further, and the above bracket and the window slides 4 or whatever the processor to processor the value changes, then that it slides forward and shows the content of the register window. So when the subroutine ends, then again it moves back and come on the same previous program run, and we can continue to operating and to executing the main program. And the next article is the example instruction set. So it is also known as the MIPS instruction set. The instruction set known as MIPS instruction set, and it is among the early RISC designs, and it is minimalistic instruction set. And what does the minimalistic, we will discuss it in the next article. Okay, this is the specimen instruction set of MIP instruction set. You can check that the categories which we discussed in the start of this lecture, that there are arithmetic operations, logical operations or instructions, logical instructions, and so on. So you can check here that the MIPS instruction set has different type of arithmetic instructions. The first one is add, and the meaning of this instruction is integer addition, that the two integer values that can be added, and for the two integer values addition, we can call this command by simply giving this keyword add. The subtract, similarly, integer subtraction, and add immediate. The immediate means the constant. Okay, so add immediate means integer addition, that is the register plus constant, the value of a register plus a constant. And add unsigned means unsigned integer addition. The normal add, it may be signed or unsigned, because here the flexibility is with the programmer. But when we have the add immediate, add unsigned or add immediate, if we are dealing with the unsigned integer addition, so we can our data type is unsigned integers, so we can instead of calling the add instruction, we can use the add unsigned instruction. Similarly, the subtract unsigned and the add immediate unsigned. Immediate wherever the word immediate is used, so you can easily remember this, that we are talking about something which is called constant, some register value plus the constant. Move from coprocessor, that access coprocessor register, and we had discussed that there are multiple type of coprocessor, math coprocessor, word coprocessor. So whenever we invoke the coprocessor, so move from coprocessor. And then multiply means integer multiplication, and multiply unsigned means unsigned integer multiplication. Divide means integer division, and divide unsigned means unsigned integer division. Similarly, move from high and move from low means the access high order register and access lower registers. So you need to be careful about these commands, that whichever scenario we have, so almost we have a dedicated command for this in the MIPS instruction set. And till now we have seen two broader families. One is called arithmetic instructions, and the other one is called logical instructions or Boolean instructions. And these Boolean instructions include add, which adds the logical and not add, it is and logical and two registers, that the and gate, which we studied in the chapter number 2. This is the same function. Similarly, or logical or two registers. Here again we will perform an or operation between two registers. And third one is and immediate. And immediate means ANDing of a register and a constant. And register or immediate means or of register and constant. And the shift left logical means shift left shift register left n bits, and shift right logical means the shift register right n bits, and n are the number of bits over here. Okay, and moving forward, we see that there is another group of command which are called data transfer. Typically this type of commands are being handled by the microsequencers, because these commands include load word, that load register from memory, and store word, store register into memory, and load upper immediate, place constant in upper 16 bits of the register, and move from coprocessor register, obtain a value from a coprocessor. So these are the different specimen commands which are the part of the data transfer commands. And similarly, we do have the conditional branches and unconditional branches. Next, so conditional branches, the commands include in the data set of the MIPS processor, which is related to the conditional branching, is the branch equal, which shows that the branch if two registers are equal. Branch not equal, that jump to branch if two registers are unequal. Set on less than, it means that compare two registers, and set less than immediate, compare register and the constant. And set less than unsigned, compare unsigned integers, and set less than immediate, compare unsigned register and constants. So this is a complete business package, you can say, that this MIPS instructions. So far we have discussed arithmetic instructions, and then logical instructions, data transfer instructions, conditional branches, and now we are coming to the unconditional branches. So the first command in the unconditional branches is called the jump instruction. So jump instruction tells the computer that go to the target address, and that is why it copies the content of address register and directly jumps to that place, and jump register go to address in the register. So in the first command and the second command, the difference is this, that the in the first command jump we are explicitly giving him the target address, and in the second command jump register we are asking him to check the contents of a register, and there it will get an address, and follow that address and jump to that address. Similarly, jump and link, this is used in the procedure call, because we have different remote procedure calls in the operating systems. If we do need the support from the remote, now more than very sophisticated tools have been invented, but in the starting days this remote procedural call was very popular. So okay, jump and link is the jump and link, it is the procedure call, it is the part of procedure call. And now coming to the arithmetic of the floating point instruction. As we have already discussed that there are two type of registers available in the microprocessor. The one is the general purpose registers, and the other one is the floating point registers, or the floating point instructions. So let us further discuss it, that all the commands which we have already discussed in the same lecture, and they are replicated again with a keyword FP, and FP stands for the floating point values. That means FP add, FP subtract, FP multiply, FP divide. So all this means that floating point addition, floating point subtraction, and floating point multiplication, and so on, etc., etc. So and the floating point add double means double precision addition. What does double precision addition? That the addition will be having the 18 walls, that 18 okay, and data transfer, and the next one is the data transfer instructions, that load word coprocessor, load value into floating point register, and store word coprocessor, it store floating point register to memory. So these are the data transfer instructions. And the conditional branches include branch floating point true, branch if floating point condition is true, and branch floating point false means jump to the branch if the floating point condition is false. That a decision box in the processing will come in the floating point values, and there these commands can be used and can be controlled. And the floating point compare two floating point segments, and floating point camera doubtable, floating point compare double. So compare two double precision values. This command, this syntax FP compare double, compare the double decision value, compare the floating point compare double means the compare two double precision values. Okay, and okay, no need to understand or to memorize the syntax and their meanings. You just must be familiar with this code, and must be able to use it whenever you have to deal with appropriate type of data. so then you can use it. And the aesthetic aspects of instruction sets means its elegance, that it must be balanced, no frivolous or useless instructions, that it must not be overpopulated or crowded. And the next so this is the if the instruction set is balanced, then we say that this is an elegant instruction set. And the orthogonality, another aspect of the instruction set, which is the aesthetic touch, is the orthogonality, that no unnecessary duplication, that there must be one and only one command to perform single type of task in the computer. So no unnecessary duplication and no overlapping among instructions, that this must not happen in the computer, that one instruction can do this work and the other one can also do this work. So no overlapping must be in the instructions. And the principle, the last one, almost last one, is the principle of orthogonality. And the principle of orthogonality specifies that each instruction should perform a unique task without depending or on or overlapping, without duplicating or overlapping the functionality of other instructions. Okay, so this is the principle of orthogonality. And after this we have to come to the condition codes. So there are extra hardware bits not part of general purpose registers, which are set by ALU on each instruction. And these extra bits indicate the overflow, underflow, and other exceptions which are tested in conditional branch instructions. So to record these condition codes, we have the special hardware available. An example of the condition code, you can see here that we are comparing the two registers R4 and R5 and branch to lab 1. That one branch I have named him anything. So I will write capital M, and I hope that the conditional sorry, I will write the CMP, that the condition code, and it will start comparing the register, the contents of the register, whatever register number I have given in after this argument. Okay, and BE means the branch to lab 1 if condition code specifies equal, that if it satisfies the condition, then it will begin the lab 1 branch, and it will move 0 value in register R3, otherwise place a 0 in register R3. So program continues at this point. Above code places a 0 in register 3 if register 4 is not equal to register 5, that it will compare the contents of register 4 and 5, and if they are not equal, then it will place a 0 in R3 and otherwise give a lab 1, and it will run the lab 1. Okay, so till here, till this time, we have completed our chapter number 5, and you can if you think that we are running on the same mediocre pace, then okay, otherwise let me know in the question answer session, and we can further increase or decrease our speed with you guys in the interactive session. And once again, happy learning, and stay tuned with me for the next lectures to come. And until that time, let me finish this lecture, and our time is also about to finish, and Allah Hafiz for now, and inshallah we will meet with the part B of the same lecture number 5. Assalamu alaikum wa rahmatullah.